Alright, so the fourth problem is pretty interesting. We are given a chessboard, 50 cross 50 chessboard, and we are asked to uh, move knight. So each test case will have a knight with a particular position on the chessboard and a few pawns as mentioned in the positions array denoting the position of each pawn. Alright, we have two players, Alice and Bob, and each player can choose a pawn and capture it. Alright, in fewest possible moves. Okay, and the same thing is going to be done by Bob. In the process, it's mentioned that a knight may pass other pawns without capturing them, right? So, for example, if I have this pawn and this pawn, right? I can choose to capture this pawn. If I choose to capture this pawn, then I can move here. But since I move here, it doesn't mean that I'm going to capture this. I'm going to only capture the one that I have chosen in two moves. Right? So that's what that statement signifies. Here, Alice is trying to maximize the sum of the number of moves, and Bob is trying to minimize them. What we are interested in is that we have to uh, get the maximum total number of moves that Alice is keeping track of, such that both players are playing optimally, right? So firstly, we have to see where this problem is going. Right? So we have to do some right away. We can think of DP, right? But if we do DP straight away, we have to do a lot of things. Firstly, we don't know where the knight must move, what are the least number of moves for each pawn to be captured, right? So that is the first thing. So that should also hint us towards pre-computing the least number of moves from a particular position, right? So if we think of where the knight is going to move eventually, we have to understand that knight is always going to move towards a pawn position, right? Because the goal of the knight is to capture the pawn. So here in this example, this is going to move here in two moves, right? But eventually it's going to move at a pawn position. Similarly, from here, it's going to move here in whatever number of moves, but it's going to move here, right? So the knight is always going to move to a pawn position in certain least number of moves, right? So if we pre-compute that, what is going to be the least number of moves from here to here? What is going to be the least number of moves from here to here? What is going to be the least number of moves from here to here? In that case, I can do the DP part easily using this pre-computed part, right? So we are going to do that, but how we are going to do that? We can do a BFS, right? A breadth first search. So how a knight is going to move? It's going to move either in this, this, this position, this, or this and this, right? So these are the uh, position that the knight can move. So I'm going to do a breadth first search. I'm going to have a queue in which I will initialize this position where the knight is currently, and I'm going to find the least number of moves to reach each cell, right? So for this cell, what's the least number of moves? Well, I can move. Let's see. This can move here, 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 and here. I want to reach here. This position can be reachable, is reachable from here, or let me mark this as plus, plus, and plus, 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 right? And similarly, we can do that BFS. How can we reach here from, I mean, you get the idea, right? We are doing a BFS, right? So eventually I'll have from here what all moves that will take for each cell to be reached, right? I'm going to do the same thing for each pawn as well, right? Because eventually the knight is going to capture a pawn, and from that pawn position it's going to go to the next pawn, right? So that's what we are going to do. I'm going to have a vector of vector which is going to have a visited, which is visited, and this is going to be of length 50, comma vector of int 50. Oh my bad. This is 50 and 50, comma 0, initialized with 0. So each position is going to have a 50 cross 50 board with each uh, value being the least number of moves to reach from this position to this position, right? How many of those board do we require? We require the number of pawns is going to determine the number of boards we are going to require, but there is a catch because the initial knight position is also going to have a board of 50 cross 50 with the least number of moves for each cell, right? So essentially we are going to have a vector of vector of vector of int, and this is called least moves. Let me give the n from position size, and this is going to be n plus 1, y plus 1, because we want 1 for the knight as well, and this is going to be initialized with vector of vector int 50, comma vector of int. This is also 50, comma 0 initially. All right. I'm going to do a BFS. So I will call the BFS first for the first uh, knight position, right? And then for each pawn. So for this one, I'll do it like this: BFS from knight, initial knight position to each pawn, or actually don't need to mention for each pawn because it's going to find it for every cell. So I'll call it BFS least moves because that's going to be populated here. I need positions. Actually, no, I don't even need positions. I need the initial position, right? Kx and ky is the initial position, and that's probably it. I'll have a vector of directions. Why directions? Because I want I know that this knight can move in the positive direction, that is +2 in column, +1 in row, or a +2 in column, -1 in row, or a -2 in row, +1 in column, -1 in column, and so on and so forth. So that's what I'm going to define it here. Alright, either 2, 1, or I'll have 8 such possibilities: 1, 2, 3, 4, 5, 6, 7, 8, and this will be either 2, 1 or 2, -1, or a -2, 1 and a -2, -1, or a 1, 2, 1, -2, or a 1, -1, 2, -1, -2. Alright, so this is the directions. Since this is global, I don't need to pass it here, but let's do the other things as well. For each pawn there is going to be a BFS. Also, by the way, a visited array is also going to be passed. BFS from each pawn. For that, I'm going to have a traversal on positions array, and I'm going to also reinitialize visited as well as, right, because this will be changed when I do this BFS, so I have to clear the changes. So I'm going to redefine it here. We can do it other ways as well, and BFS is going to have an initial position as positions of I, and 1. Finally, least moves. So least moves as it is, and visited as it is. Finally, let me right now return 0 at this point so that I don't make any silly mistakes. I'll do the logic for BFS right now. Int x, int y, vector. Let me copy it. Right. Least moves, I'll pass reference. Similarly, visited. So this is visited array. At this point, I'll define a queue inside which I will have a pair of integer because I'll have a pair of an x and y coordinate. I'll initialize queue with x comma y. I will mark this as well to 1. Now I will traverse until queue is empty. Alright, I will do it level wise because for each level I'll increase the distance by 1, and that's why I'm going to have a level as well. Level, which is basically the number of moves. So let me call it moves instead. At this point, I'll get the size of queue.size, and for each level, this is the loop that is going to run, and I'm going to get position x from queue.front dot first, and second will be my second, I'm in position y. Q dot pop, and size will be reduced. All right. At this point, I'll start traversing to the neighbors that is reachable, and that is going to be dir dot size. It's going to be basically this: many neighbors, I plus plus. I'm going to get the new position x, or new x, let me call that. Uh, this will be position x plus direction of 0, or I 0, and the same thing is for position y and new y. At this point, I'll check if new x is greater than equal to 0 and new x is less than 50, and new y is greater than equal to 0 and new y is less than 50, and finally if it's not visited. In that case, I'm going to visit them, and finally I'm going to push it. But before that, I'm going to update the least moves as well. uh, which is going to be what index. This is tricky. I'll also have to pass the index for the least moves, right? Because which index I'm updating, that I'll have to determine here. So this is the index for the first index, will signify the 50 cross 50 board of least moves for the initial knight position, and the rest will be for the pawns. So alright, this is the index. I'm going to update it for which all cells, that is going to be defined by new x and new y. Alright, and this is going to be initialized with moves, and it's going to be q is going to be pushed with values new x and new y, so that we can continue DFS from there. And finally, when I change the level, I'll increase the moves. Alright, and I don't need to return anything. This is void because least moves will be populated here. Let's see if this works. If this is working, I'm returning 0 here, so answer will be obviously wrong. Okay, this seems to work. At least there is no syntax error. Now I'll do the DP. So I have the least number of moves for each position to each pawn position. I can choose any of them, but I have to choose it such that for Alice it's maximized, for Bob it's minimized, right? So essentially I'm going to have a DP in which I'm going to pass positions, alright, which is visited, I mean which index is visited, right? For example, I capture, so in this example, if I capture this pawn position, then I'm going to visit it. The next thing I capture, this pawn position, I'm going to visit it. The next one is this, I'm going to visit it, right? In whatever order, I have to have a state where this is visited or not, alright? But if I have a vector, I won't be able to minimize it, right? But I have to, if I don't minimize it, this is going to give us TL. So I can show you that, but to save some time, I'm going to use bit masking here because that's how we are going to solve this. Because if you look at the constraint, it's only 15, right? So I can have a bit masking of 15 length and minimize it so that this can pass. So this is essentially going to have least moves because the pre-computed values needed, and finally 0. So index is not index but 0. So this is going to be needed. This is pass TP vector of vector of int for positions, index least moves. So let me copy it, and finally bit mask. I'll call it bit mask, or I can call it visited as well. Okay, if all of them is visited, all of them are visited, then visited will be equal to 15 or whatever the length is. That I can do it easily by checking if visited is equal to 1, I mean 2 to the power position dot size minus 1, right? So this is what will define my base case, and at this point I'll return 0. Otherwise, I will have answer initialized here, I mean declared here. Actually, I also need to pass the turn, right? Whose turn it is whose, right? So at this point, if 0, then 0 is the number that will signify Alice's turn, and 1 will signify Bob's turn. So is this Bob's turn? Actually, let me call it turn. Or is, yeah, turn. So if turn is 0, then it's Alice. Maximize here, else minimize here, and finally return answer. So since here we are maximizing, I'll initialize answer as int max min, and similarly here we are minimizing, so max. Finally, I will choose a pawn to be captured. Uh, let's say that will be positions of size, but I can only choose if this is not visited, right? So if visited, this current index is visited or not, how will I determine that? I will determine it using the bit masking technique. If this is and with 1 and it is 1, this means that this is visited, right? Continue in that case. Otherwise, answer is equal to maximize of answer comma dp of positions comma I plus 1. So the next index, I'll move to the next pawn to capture. I'll toggle the tone because it will be Bob's turn next, and least moves will be as it is, and finally visited will be as it is. Instead of visited won't be as it is because I have to toggle the bit for this particular index I, and that is going to be nothing but this, right? This is how toggle works for in-bit masking. And finally, I'm going to do the same thing for Bob as well, but just the opposite. So this will be minimum, and that's pretty much it. And uh, one thing that we are missing is adding the moves, right? So for this one, the move will be what? From least moves of index positions of I. So this is what signifies the from, where we are coming from. So this will be the first index, and the second and the next two will be the positions of the pawns, right? Which will signify the number of least moves to reach this position position of I0, and this pawn will be captured in this least number of moves for this particular from this particular index. All right, so this is what it signifies, and this is the same thing that will appear here. All right, so that's pretty much it. Let's see if this works or not. Okay, it does. Let's submit and see. Okay, so now it doesn't work, right? But there is a reason I did take visited as a bit masking instead of doing a vector of int, because I need to minimize it, and this is a state. So how we are going to minimize it? This is what is changing, and this is what is changing. Just be careful, because turn is not, you know, uh, changing as such as a state, right? Because a game when started is going from Alice to Bob and from Bob to Alice. It's not like Bob can start first as well, uh, instead of Alice, right? So turn is not a state, so I don't need to take a 3D vector, but a 2D vector will just do fine. Or instead, let me take unordered map. That will be faster. Not faster in the sense of time complexity, will be same, but just coding it up will be faster. So this will be cache. Let me copy this for the argument, and I'll check here if cache dot find uh, visited. If it's not, then at this point I will initialize or resize the vector, essentially initialize the vector with the positions size, because the index is the next, right, state, and visited is already the state inside vector, inside map. All right, so this I'll initialize it with -1. If cache cache of visited of index, if it's not equal to -1, in that case please return visited index. All right, and I will copy and populate it with answer here. And finally, I'll call cache for each DP call. I'll pass cache for each DP call, and that's pretty much it. Let's see if this works. The time complexity, okay, it doesn't. Oh, my bad. I'm not returning it here. This should be returned. And let's see if this works. I guess I should have submitted it already. The time complexity can be a little tricky. So if I try to find the time complexity, I do it stepwise. Here, the time complexity will be a single BFS. A single BFS will be 50 cross 50 is the board, and for each, yeah, that's pretty much it, right? Uh, because we have a visited array, we are not going to revisit a cell again. So 50 cross 50, that's going to be 2500, and for each BFS, and the BFS will be called for each pawn as well. So into n plus 1, this is the overall time complexity after forming the BFS. Now comes the DP part. The DP is going to have a state of index and visit it. So uh, this is basically n, right? And this is what we are choosing and capturing. So we have either we don't capture it, we capture it at a single decision, right? So 2 to the power n is going to be that, and since we have visited as well, so this is essentially going to be the uh, approximate time complexity and the dominant part of the overall time complexity as well. And since it's passing, let's see what n is. N must be small, and that's 15, right? So n to the power 15 is what? Let's see, 2 to the power 15 is doable, right? Definitely doable. So, all right, so this is the time complexity. This is the fourth problem. Uh, I know it's a little too long and lengthy, complicated as well, but this is basically different concepts applied into a single problem, right? And yeah, thanks, guys.